Button is pushed.
Good evening, everyone, and welcome to our senior capstone final presentation. We are the Human Gait Emulator team, and we are comprised of myself, Sarah Struble, Adam Novak, Michael Bender, Sarah McInnes, and Brister Jones. Before we describe our project, we must first introduce our sponsor, Gait Industries. Gait Industries is a company that manufactures worker safety equipment, specifically the PAS sensor. The PAS stands for Personal Alert Safety System, which is a clip-on device that registers the movement of the wearer. The PAS sensor sounds an alarm if the worker has stopped moving. Since this product is used by firefighters in the midst of duty, it is important for Gait Industries to ensure the reliability of the PAS sensor. Gait Industries tests each sensor they produce on an individual basis and manually to ensure that their products are reliable. Before they enlisted our help, this was done by 2 or 3 employees who would just walk around clipping the sensor on their hip and would mark down whenever the sensor failed or passed and write down if the sensor was acting correctly or not. As you can imagine, this is a very time-consuming process and a bit of a waste of personnel. So Gait Industries reached out to Grove City to have one of their senior project teams create an automated solution. We were given a list of requirements that were necessary for our project. First, we were to develop a system that could sense if a person was actively moving or staying in one place using a sensor attached to the hip. Also, we were to use this system to collect accurate data for the human walking motion y-axis, up and down, and x-axis, side to side. Lastly, we had to develop a system to replicate the motion for the up and down gait and a system to replicate the side to side gait of a walking human being. We were also given a list of requirements that were not mandatory for the project but would still be helpful to our sponsor. The most important of these, the should requirement, was to develop a system to replicate the motion for both the up and down and the side to side, as experienced by the sensor. Once we finished all the requirements previously listed, we were to use our sensor to collect accurate data for the human walking motion of the z-axis, so forward and back, in addition to the previous x and y-axis motion, and develop a system to replicate the up and down, side to side, and forward and back motion. Finally, if we were able to, we were to develop a system which could sense whether a person was actively running, walking, or staying in one place. Now that we had our initial requirements, it was time for us to meet with Gait Industries so they could directly communicate with us their needs and desires for our project.
So, as Sarah said, we wanted to meet with Gait Industries before we began any real progress on our project to make sure that we both had a solid understanding of the end goal of this product. It's a good thing that we did because the first requirement that Sarah mentioned, which was to develop a system to measure human motion, was actually already accomplished by Gait Industries' PAS sensor, which you can see in the top corner. So we were able to use that to clear a lot of the difficulty of trying to create a sensor to test human motion and creating this mechanism to emulate human motion dependently, which would have been outside the scope of a senior project. The PAS sensor was able to use this program which was supplied to us by Gait Industries and was able to give us information on the position and acceleration. The file on the left, you can see the WFD file. If you just change the extension to CSV, you can then read that file with any sort of coding language, and we were able to do that, as I will show you later, to make motion commands for our robot.
So our original idea for this Gait emulator was to build the entire device ourselves. So starting from scratch and everything, all the different axes. And while as strange as it sounds, we started by disassembling a printer, because within a printer, they have multiple axes to control the various parts in it. So we figured we could take some inspiration from what's already there. Here we have some of our initial brainstorming for how we would accomplish the various axes. So for example, for the vertical axes, we have a pulley, we have various implementations of a pulley system where we would attach the sensor to it and pull it up and down. We also had a screw system for the same, for the vertical system as well, pulling up and down. Horizontally, we considered some form of belt system where the sensor could either rest on it or clip to it and move it horizontally. And then one of our final ideas, similar to how a claw machine works, we considered how you have two perpendicular bars that would move in the horizontal direction, and then some form of almost like, well, a claw machine where it can go up and down like that for the third dimension. Here we have our initial design for our Mark I design and our Mark II design, where our Mark I was a singular horizontal axis going back and forth with the belt design I mentioned, and with Mark II being both the x-axis of the belt design and a vertical axis of a pulley design to accomplish the two axes. To control this, we would have a control panel where Grace Industries or someone else, the user, could input what gate they were hoping to accomplish to the microcontroller, which would run the gates through the motors with the robot body, and then display out to the user either what the gate is or any other information that is deemed necessary. And then physically connected to that would be Grace Industries sensor that Adam mentioned, which would then be able to be interfaced with the motion logger software that Adam mentioned that could read all the information from it via Bluetooth, which would then we'd be able to use that information to graph it and see how each of these axes move. For the microcontroller, we ended up between two final decisions between them of using the Arduino Do and the NXP Freedom Board. The reason between these two was because for Arduinos, they're normally used for projects of this type and others, and they're very flexible for this. The NXP board is actually used in the path sensor, and so it is something familiar to Grace Industries. So if anything were needed to be done with it, they are already equipped to do that. As you can see, based on these, it's a little confusing with all the information there. But the Arduino Do actually has more digital output pins as well as higher amounts of memory and SRAM. But because of its familiarity with Grace Industries, we chose the NXP board. Additionally, because while the Arduino has more memory, more storage, and more output pins, the sheer number was not necessary for what we were trying to accomplish. And here we have what we finally ended up with by the end of the first semester, halfway through. This was a linear motion rack, and this is actually one we purchased because while we were considering building one ourselves, we were able to talk with the mechanical engineering department, and they helped us realize that this was a much cheaper to purchase it than to even try to manufacture it, just based on how it was. The actual speed for this linear motion rack was an inch per second, which we deemed as being not fast enough and didn't have the needed acceleration to register with the path sensor. So what we were planning to do the second semester was increase the gear ratio in the hopes to increase that speed and improve it in that way.
So, this is about the time the second semester rolls around. We look back and we go, well, we have a lot of data for the path sensor, so that's good. But as we were discovering, all of the data was bad. As Sarah mentioned a little bit later, there was a problem with our data, so we had to retake our data. So that was fun. And as far as the physical system, we had a single axis of motion that was too slow and needed updating. We looked ahead at our goal and said, all right, minimum, we're trying to make something that has two axes of motion, both for our satisfaction, and also we wanted to actually make something that was going to be beneficial to Grace Industries. With our current trajectory, we weren't exactly seeing an end in sight. So we considered what we could do from here. We could continue construction. As I just mentioned, this did not seem to be a very viable option for us. So the next thing that we were thinking about was, what about purchasing something? We had not spent much of our budget at this point, so we started looking around. The first thing that we looked at were gantries, which were, like Michael talked about, intersecting rails, like you would expect on a claw machine, where you have two rails intersecting for the X and Y, and then you have the vertical rail for the Z axis. Unfortunately, the least expensive one was $500 outside of our budget range, and went up to about $5,000. So, not really what we were looking for. The one that did get back to us about halfway through the semester was within our budget, but this was way too late to be used to us. We started looking instead at the FANUC robot, which you may have seen earlier with presentations. This is what Grove City has on campus. It is a much larger version of a robotic arm than what we ended up with. But this would be something that could meet every single one of Grace Industries' needs. It would have the accuracy of controlling every single motion that it has. It could have the weight limit to test 1-2 dozen path sensors at once. Only problem is, it has a price tag. Very large one. Grace Industries was not ready to make that sort of commitment to buying a FANUC robot, and it was also being used, as you saw again earlier, by another city project, so we weren't able to get our hands on it. Finally, we found in a dark corner of the internet, you will see the UARM Swift Pro down here. This was surprisingly everything we could ask for. It was within our budget. Speeds up to 100 millimeters per second, which was well within what Grace Industries needed. It had 1 ounce more than the maximum weight of the heaviest Grace Industries sensor, and repeatability of 0.2 millimeters. So we purchased this thing and actually began our senior project. So for controlling the UARM came with a GUI-based interface called the UARM Studio, which had 3 different methods. Blockly, which is a drag and drop programming type block language, but unfortunately for us, it was a little too simple to do what we needed, so we dropped that. Control is where you sit at the robot and you control it. Since Grace Industries was looking to get into full automation for their testing suite, this didn't make a lot of sense either, so we skipped over that. Teach and play seemed very promising, but unfortunately it reduces the speed of the robot to about 25%, and also the motion mapping is not the best. So if you make a semicircle, it'll look more like half of an octagon than an actual semicircle. It'll make a bunch of points and connect them with straight lines. So we dropped that. Next up, we looked at the software libraries, since those seem to be the best thing. Python was where we went to first, since that is very easy to use very easy to get on computers that do not have the language installed already, and our familiarity with the language already. So with that, we were able to, on the left, the script actually will take data from the CSV files that we got from the path sensor itself, and we'll take those and put those into motion commands for the robot, as you can see on the right side. Not very interesting, but this is the motion of the sensor as seen from the sensor.
Okay, so after we got all of that coding and stuff kind of set for our tracks, we ended up making a frame. This frame covers the entire range of motion of the robot. This prevents it from hitting anything in its environment. It protects the robot itself as well as those around it. And Grace Industries actually requested this just for safety reasons. This was made by our hardware lab, or helped by our hardware lab. We also spray painted it blue just to kind of make it very obvious that you are not supposed to go in that box. So here is an LED indicator block that we actually made here. The outside is a 3D printed case that was printed in Grove City. We have a 3D printer here. This case encompasses 3 LEDs, a red, green, and yellow. These all indicate different states of the code. So yellow indicates that either it could fail or it could not fail. So either the alarm will go off or it won't, and it'll still pass the tests. Red means that the alarm should sound. If the alarm does not sound, then that means that it has failed and that pass sensor is not viable. The green means that there is no alarm, and if an alarm sounds, then it will also fail. As you can see, there's a diagram at the bottom of the circuitry inside. We found out that our U-arm output did not have high enough current on individual outputs to run the LEDs. So we had to hook it up to a 5-volt output from the robot directly to switch with the transistor when that signal comes in to light up that LED with the proper amount of current. So we had a few setbacks, as Adam mentioned. So we had some mysterious behavior with the pass sensor. We got the results out from having Brister and all of us walk around with this pass sensor clipped to our head, and we looked at the graphs, and the graphs came out really funny. While looking at them, we realized that the y-axis looked more like a combination of the X and Z, and that's exactly what was happening. So we reached out to Grace Industries, and they provided us a new code, and that fixed it right away. So we were very thankful for that. The next thing we came into was while we were programming the U-arm itself, we saw a set polar, which by the name, you'd think it's using polar coordinates. However, we found out it's more of a cylindrical coordinate, which makes the name very deceiving. We didn't find that out until we started trying to code, and the robot fell on itself. This is also caused by if you have more than 3 motion commands, it will collapse on itself. So that was not viable at all. Instead, we just went to the use of Cartesian coordinates, and that fixed it. The last issue we ran into, which we ran into like last week, was a firmware issue. The U-Factory updated the firmware, and this firmware claimed to be faster and better and just all over great. We updated it, and it slowed our robot down. It took about 5 seconds for any of the motion commands to load, and it would time out before it even got there. So that was just a lot of communication issues, and we had to talk to the U-Factory, see what was going on there. In the end, we ended up reverting it back to the old firmware, and it's working fine now. And eventually, if we do get that firmware fixed, or if we contact U-Arm Factory again, get that all solved, we might be able to update that firmware and get it even faster and smoother. But for now, we're just reverting back to the previous. So here is a demo of our robot doing a walking gait. So this is directly from results from Brister, our next speaker, his walking gaits. So I know it looks a little funny when you're looking at it. You're probably like, that's not what my hip looks like. But in fact, this is the acceleration that the pass sensor receives. So it is directly correlated. And whenever you compare the graphs that this produces compared to what was produced when Brister was walking around, they're very similar, if not identical in some spots, which makes it a very good representation. And as you can see, since it is a walking gait, it did not alarm at that end. So that is very good. That did pass the test. And here's a demo of it standing. I know you're thinking you're standing, you're not moving, but when you're standing here, just like any of us, we're standing here, we move a little, you shift from foot to foot, bounce on the balls of your feet, there's a little bit of motion in there. You would think that that would make the alarm not go off, but in fact, it's not enough acceleration to keep it from going off. I know this sounds annoying and loud, but that's a good thing because it'll alert people to their location. And this is also a quieted down version. The loudest version would blow this entire room. It's crazy. So that is just the demonstration of the standing robot, and that is, again, directly from Brister's motion.
Alright, so looking at our budget, you can see we had one rather large item that dwarfs them all. That's the UARM itself. Since it solved the vast majority of our problems, it took up the vast majority of the budget. The other costs, the gear rack and servos, were more research costs in that first semester as we were getting our bearings, and then lumber screws and the 3D printing are making the box around it and the lights and such to get it working and looking good there. As for the sensitivity analysis, that was 85% of our spending was the one item. Then you've got 13% on research and 3% on the kind of finishing touches. Note 85% of what we spent a total of 58.9% of our budget, so we came in well under budget, but that was the big ticket item. Had to get a lot of approvals through for that one. But going forward, so future usefulness of the project, it works for a proof of concept. It shows that you can automate the testing, that it can mimic the motion, and so that you can take that going forward. And it also can be used for preliminary testing if you want in the lab to go, okay, this is a new design, does this have any major issues? This can check that, but it isn't going to reach the safety standards that the past sensors are held to. So where you can go from there is improvements towards looking at either a FANUC robot or a more precise arm that could either be testing multiple at once or have more precise controls. One of the limitations of the U-arm is that it can go from point A to point B at a set speed, but you can't set the acceleration to get to that speed, which limits how precise your mimicry of motion can be. So that's something that with a FANUC robot or other arm you would be able to get. So in conclusion, it was a success. We came in under budget. As they alluded to earlier, our graphs do look similar to the graphs of human motion from our tests, so it is properly mimicking. And we met all of the must requirements. We met the should requirement. We didn't meet the coulds, but machine learning and 6 axes of motion were a little outside of the scope and budget of our project, and so bridge too far. But overall, completed everything that we set out to do. So we want to acknowledge Mr. Gillette and Mr. Peisch for helping in the lab, our advisors, Dr. Bright and Dr. Walker, and Grace Industries for supplying us with their past sensor, the NXP boards, and just helping us understand what they needed and helping us through when we ran into issues, also specifically our contact Matthew Ross. And with that, are there any questions? Yes.
Does the full motion of your arm really represent the full accelerations that you're measuring? I see a person walking, there's already a translation that you're doing. And is there anything that's part of your motion of the arm that has to sort of like be a reset or something like that to mimic the full acceleration?
Sort of. Like, when we compared the graphs, they were close enough to be what we could manage with our budget and our time constraints and how we went with the project. That level of precision, I don't think is going to be achievable by something of this caliber.
I think if our robot spun all the way around, it would be a little bit better. But in our price range, we couldn't get something that spun the entire rim around. So it did have to reset a little bit. But since it was acceleration only and walking, as long as there's acceleration, that pass sensor, the alarm will not go off. That's kind of what it's focused on, less on the actual distance and motion itself. It's all just acceleration. That pass sensor takes and says, is there acceleration? Okay, then I'm not gonna, make my alarm happen. But if there's not any acceleration or if there's very little, then that's what causes the alarm to go on.
So it's not sensitive necessarily to
But if you do look at the, there is like an X and Y and Z, that kind of is affected, but the orientation overall does not matter in the grand scheme of it.
The alarm will still go off no matter what the orientation is. The only difference is the data that we collect. And by difference in the data, I just mean that the data that you would see in the y-axis would then be in the z-axis wherever you orient it.
And another thing is that pass sensor, depending on how like the firefighter or whoever's wearing it is wearing it, they can either clip it onto their shoulder, which if they're wearing a jacket kind of like I am, they'll clip it sideways. However, if they clip it onto their pants or on their belt, it will be up and down. So that'll already be adjusting that. So we had to kind of test for all different angles of that.
Yes.
You guys mentioned using the Fanuc robot, but you said another team was using it. Did you look into using the Canova robot, the other arm manipulator in the Robo Lab at all?
Actually, yes, we did. We talked to Dr. Allison, who is the one who kind of is behind all of those, and he said, unfortunately, with our time constraint, it would be hard to directly convert from what we were getting from the pass sensor to that robot, since it's more kind of a play. I don't know if you've worked with it before. I think, yeah, you were in my class then. But it's a lot harder to get precise movement on that. Whenever you're trying to pull it in from something, there's not really an easy coding language for it. It's just that the 3D model that we played with in class. So unfortunately, it was not quite viable for what we wanted. We tried that, but you know, again, it was a very expensive robot still. Not as expensive as the Fanuc, but yeah, we tried that. It didn't work. Any other questions?
All right, thank you, folks.